Thank you very much for the introduction. I would like to make a quick poll here. Who has already heard of core site components over here? So there are some people. So my talk will be mostly about these components. We are going to use them for preventing software attacks, but it can be used, for fuzzing, like it has been shown in the yesterday talk. By using Intel PT trace, they used Intel PT for fuzzing. Similarly, core site components provide the same informations, and we can use to do the same things as well. So first of all, who am I? I am a PhD student at Centrale Supélec. It's a French engineering school. So here is a QR code you can scan to get in touch with me if you want. So this work is done in a frame of hardware project. You can find information on the link over here. So let's get to the chase of this talk. I am going to present you the motivation behind this work. Then I will explain you what are core site components, how are we going to use them, and then I will talk about how we are going to use these components to prevent software attacks and how to improve software security. We are targeting the Zinc system on chip. I don't know if you are aware, if you are familiar with this kind of system on chip, but I'm just going to show you some details about it. So we have over here we have 2 Cortex-A9 CPU cores, and we have an FPGA part. We have some hardware peripherals that we are not taking care about this stuff right now. But well, what we want to do is we want to protect software that runs on this CPU core. So we are considering only a single CPU core in this work. And how we are going to prevent software security attacks? It is by implementing dynamic information flow tracking. So what is an information flow to start with? An information flow is a transfer of information between 2 information containers. Depending on which level you are looking, we are looking at the low level, information containers can be registers, memory addresses. If we look at the application level, it can be variables, constants. If we look at the operating system level, it can be files. So just to give an example, on the application level here, we have four information flows. On line 2 and line 3, we have information flows from constants towards variable. On line 4 and 5, we have information flows between variables, between A and W, B and X. So the principle is to attach a tag, a metadata to the input. So here we attach a color just to show the metadata. We attach a color here. So C1, C2 and C3 are the inputs. We attach some colors to them, and when the program gets executed, we propagate these tags. So at the end of execution, we have 2 outputs, C4 and C5. C5 is tagged red because it contains information that comes from C1. C4 is tagged green because it contains information flows that comes from C2 and C3, which were tagged yellow and blue. So this is how we get the green tag. So the idea is to monitor the information flows during program execution and check for security policy violations. So here I'm just going to give you a simple example. It's really simplified to just show you how it works. So here we have a memory overflow attack, buffer overflow attack here. So we have an index that is typed by the user from the standard input, and well, let's consider that the user types buffer size +1. So this is the state of the system at initially. So we have the CPU registers over here, we have the memory addresses over here, and we are showing the tags in this column over here. So initially everything is fine. This is why they are tagged green. So when we are going to execute our program, how the tags are going to evolve. This is what I'm going to show you now. So as the input is tainted because we consider it insecure, non-secure, unsecure, R1 is going to be tagged red as well. It's going to be tagged unsecure as well. Similarly, when we try to load into a register a value pointed by R1, we are going to tag R2 as well. R4 is going to be tagged red as well because R2 was right. And when we are going to, we would like to overwrite the return address, the tag will be overwritten as well. So this is how, by checking the tags, we can determine whether there was an attack or not. So again, it's a simple example, but just to show you how information flow works. So basically, to sum it up, we have 3 steps always. We have the first step that consists in tagging the inputs. So we have to tag each CPU register, each memory address used by the application. So we need some extra storage to store these tags. The second operation is to propagate these tags during execution. And the third step is to check for unsafe uses of this tainted data. Check the tag. And we can use dynamic information for tracking to protect from low-level threats, just as I have shown you, from buffer overflows, and high-level threats as well, from SQL injection, from cross-site scripting as well. This is because we are working on a very low level. We are working on assembly instructions rather than the programming language. So we do not care about the programming language of the application, as we are working on assembly instructions. We can use it for program understanding as well, from software testing as well, but we are using here it for protection from low-level and high-level threats. So what we want to do is to protect the user level code that runs on the Linux, that runs on the Zinc system on chip. And the first problem is we need to recover all information flows that happen during an application during a program execution. So basically, we need to find out a way how to recover information about each CPU instruction that is being executed on the CPU. So a part of this answer will be recovered by core-side components. So if we have again look on the Zinc system on chip, these components are shown here on the schematic over here. So it is a set of IP blocks that provide hardware-assisted system tracing. So if we have a deeper look in these components, we have the schematic over here. So we have, first of all, we have 2 program trace macro cell components, 1 per CPU core. These components generate trace. So each time as a particular instruction is executed, they generate trace. This trace is sent towards the funnel. Funnel is just a component that merges traces together, and it sends to the replicator over here. The replicator just duplicates the trace that comes to its input towards the on-chip buffer, or we can use this component over here to send it towards the FPGA part. That is what we are going to do. So now I'm just going to show you in a little bit more detail the features provided by these components, how the trace is generated, and how we can configure these components as well. So first of all, we can use core-side components to trace all code, whether it is in user space or kernel space. We can use these components to trace the code, or we can use only a given region we want to trace, and that is what we are going to do. We only want the trace of .text section of our application. We don't want any further details. The problem with filtering all code, with tracing all code, is that it will generate huge amounts of trace, and well, we may not be able to find in terms on the FPGA side what is going on our processor. Another feature which is provided by core-side PTM component is branch broadcasting. So by default, PTM generates only trace for indirect branch addresses. It generates the branch address for indirect branch addresses. However, if we have a direct branch like over here on line 3, it does not generate the branch address. For example, it will not generate 0x84. It will generate only a packet that shows whether the branch was taken or not taken. However, we need this information to in our system. So we activate this feature. First of all, there was no support for these components on Zinc system on chip, so we added support for these components, core-side components on Zinc system on chip. This was done only by modifying the device tree file. So you can find the patch, it's available online, or you can ask me about it. Furthermore, the branch broadcasting feature was not available as well in the driver, so we patched the driver to make use of this feature in the driver. So normally it should be released in next major Linux kernel release. So there are other features that are offered by core site components that we are not going to consider in this work, that I'm going to pass by, but if you have any questions about these components, you can ask me as well. So just to show you an example of when the trace will be generated, we have an example over here. So if we have three instructions like move, add, and branch instruction, only the branch instruction will generate a trace. So we can choose to have the branch address, or we can choose to have only the information about whether the branch was taken or not. It's the branch broadcast feature that I explained earlier. Similarly, if we have a conditional branch execution, we can obtain the information as well. So if the branch is taken, we will get an E item. If a special type of packet, if the branch is not taken, we will get another type of packet to show it in the trace. Well, just a fun fact about 12. When we were trying to figuring out how to unlock these components and how to program them, the first thing to do is, to write some value in a lock access register to unlock all the other registers. So the value normally normally the value we write is 1 or well FFF or things like that. But in that particular case, it was lead speak of course site access. So well, it was thoughtful. We were happy to find this thing. So so how do we configure them in our on Linux system on chip? So first of all, we turn off the second CPU to make sure that only the program will be run only on a single CPU core. Next, we program the core site PTM components. So the mode file over here will allow us to write the features that we are going to use. For example, over here we just activated the branch broadcast feature by writing 20, and we can also give the region we want to trace. So here we want to trace only the application region between 0x8638 and 0x8684. So well, we can analyze our code.txt section and we can get this region easily. Once the PTM components are programmed, we can enable the trace sync. So either we want it on the on-chip trace, or either we want to recover the trace on the FPGA side. So we are recovering it on the FPGA side by activating TPIU over here, and then we can activate the PTM. Then we launch the application. And once the application has launched, normally we will recover the traces on the FPGA. So this is just an application that writes some memory region which is located in the FPGA to the CPU memory space, and well, we read it to find to read the traces. So just a quick example again. It's a very simple example, but just to show you what it represents. So here we have a for loop, for example. The assembly instructions will look something like that. I have just shown you the instructions that will be in the trace. So the trace looks something like that. Well, if we look at first sight, it does not look something. It does not resemble our code. The addresses we obtain over here. Well, except for the first address over here, 8638, we can find it over here, 8638. But the other addresses, they are compressed. So we only have the shift address. We only have the value, the bit values that changes. So we have to decode it. So when we decode, we find it. The trace always start with the synchronization packet over here, which is 5 zeros or more, and we have an isync packet, a synchronization packet, which shows at the starting address of trace the address where we started tracing. So 8638 in our case. And then we have the branch addresses. We have 8654. So these are the branch addresses we are getting in our trace. So if we have another look on the trace and the control flow graph of the application over here, so what we find out is each time we have a trace over here, it means that we have the control flow. We can reconstruct by using the decoded trace the control flow graph of the application over here. So we know by looking at the decoding trace that we take this branch 10 times. And then we continued. Another advantage of these core set components is if we look at the performance overhead of these components, It's negligible because, well, because of two reasons. First of all, the configuration of core side components that we used, because we are using the TPIU component that sends it towards the FPGA. If we use the on-chip buffer, we can have an overhead. Second of all, the PTM is non-intrusive. It means that it works on the in parallel on the list of committed CPU instructions. So this in the architecture itself, we have it is done in the way that the list of committed CPU instructions will be sent also towards the PTM. So to sum up this section, well, we are going to trace only the .text section of our application. We will be thanks to core side components, we'll recover all branch addresses, which will allow us to reconstruct the control flow graph of the application. And the advantage is that they are non-intrusive, so we have a negligible overhead. So how are we going to use them to improve software security? So, well, by implementing dynamic information flow tracking. So what we needed to have is the information flows, all the information flows that happen during our application execution. Thanks to core side components, we can reconstruct the control flow graph. However, we do not know what happens inside each basic block. But thankfully, we can determine by doing a static code analysis, we can determine what happens inside each basic block of the control flow graph. So here we have I'm just showing you a few examples. So if you have the sub instruction, the first instruction over here, we can by looking just at the code, we can know that there will be information flows between registers R0, R1, and R2, and well, the tag of R1 and the tag of R2 will be merged together to get the tag of register R0. This is this is how we analyze the code to get the missing information about information flows. So this is the architecture we developed. So we are using single cortex and 9 CPU cores. We activate core side components over here. So when the trace comes out, we decode it and we store it in a memory over here. And we have a coprocessor which reads these traces. We have other components. We needed to store tags of CPU registers, which are stored here. We needed also to store tag of memory addresses used by the application, which are stored over here. And the output of static analysis is stored in the tag dependency section over here. And well, the coprocessor just propagates tags and checks if checks these tags. And if something unsecure happens, it interrupts the CPU. Stop, there is something wrong. I'm just going to give you a simple example. We tested with the proof of concept design that I just showed you. So what it does, what we want to do is we want to protect to printing any secret values over here. So it can, we are showing it just, to printing, but it can be any function that sends it towards the network or any other thing, any other function that, that sends information towards the network. So what this code does is, depending on the type of user, it opens a file. If it's a normal user, it opens a public file. If it's a root user, it opens a secret file. And well, we copy the content of this file towards the buffer, and well, we print the buffer. So what we do not want is if the user is normal, okay, the buffer will be printed. If the user is root, we do not want any secret information to be revealed or to be sent towards the network. So just showing you the content of files, here, for example, we just put some strings in the files. And well, we run here we are just running the program as a root user. So the buffer value contains MDP. So this is without information flow tracking. And well, if we run the program as a normal user, we will get the other value. Well, this is allowed. So how the information flow tracking will be used to prevent, the buffer to printing this value over here. So what we do is we launch the script that I showed you earlier that that turns that shuts down the CPU, the second CPU, that programs the core side components, and then we launch the application. Once the application has launched, it means we are starting to get traces over the FPGA part. And well, we disable the core set components after the program has started, has finished executing. So if we look at the traces, so we get some addresses, and well, these addresses are stored over here. So these are the decoded traces. The coprocessor will be using these traces to find what happens inside each basic block. So over here, if we look, well, we do not need to launch anything over here, because well, when the trace starts coming out, there is an IP that interrupts the coprocessor to start working on start looking at the traces and go finding the basic blocks. And well, here we have the traces for which it went to look for the basic blocks. For example, for the first one over here, it looks at the basic block 1. Don't know if you can look at it here, but well, I wrote the addresses in little bigger font. So well, you can see over here we get this address so in the trace we get this address, and earlier, thanks to static analysis, we already had this information in a memory section. So we are going to read this memory section and propagate all these tags. Then we will go once we have finished propagating all the tags in the basic block, we are going to read the next trace. In this case, it is 10554, and well, it happens to be this basic block 4 over here. We are going to propagate the tags for this basic block. Similarly, we are going to continue. We are going to read the trace. So it is 10578. So we know that it has, after basic block 4, it has executed the basic block over here. And after that, it executes this basic block. And just before printing, we added a check, just to check the values of the operands. So here we have, in ARM instruction set, in ARM architecture, the calling convention dictates that the arguments of a function will be in the registers. So that's why we check the tags of registers, R0, R1, R2, and R3. So R1 is the register that contains the buffer value. So over here, we can look at it's tagged R1. So when it finds out, it interrupts the CPU and the program stops executing. So well, this is what I showed just here. Similarly, we can use these components to prevent from other types of attacks, like return-oriented programming attacks or jump-oriented programming attacks. This has been done by Lee et al. In a work that was presented in another conference. So what they do is, for each function call, they make a shadow call stack. Sorry. What it does is, each time a function call is executed, this information they can obtain with the traces, and they make a software analysis that matches each branch call with the returning address. And by using this, they construct their shadow call stack. And once this shadow stack has been, and once the function returns, they check the shadow stack value with the real stack value. And if it matches, everything is okay. If it does not match, well, something went wrong. And this is how they detect the return-oriented programming attacks. So just to sum up, dynamic information flow tracking allows to prevent against buffer overflows, heap overflows, data leakage prevention, I showed you earlier, and SQL injections as well, cross-site scripting as well. We can use it to prevent code reuse attacks as well. And well, just going to, well, for those of you who have not heard of core set components, this can be a takeaway for you. You can use core set components to obtain information that changes, to obtain information about program flow changes in a program. And it is non-intrusive because there is negligible performance overhead depending on your configuration of core set components. It allows to improve software security by implementing dynamic information flow tracking, for example. And well, in future work, we will consider other debug components. We'll see how they can be, whether they can be used or not to implement dynamic information flow tracking on. So this will allow us to to port our approach on other hardcore CPUs. So I'm thanking Common Labs and Brittany region to finance my PhD thesis. My PhD supervisor Pascal Cotteret, who would have loved to be here but who could not make it, and another PhD student who is working on the software side of this topic, and my PhD supervisors as well. So if you have any questions, thank you for listening. If you have any questions, I will be happy to answer them.
So does anybody have a question for Mohammed? No? Nobody? And thanks, Mohammed.
Oh, okay.
Oh, sorry.
So you said that the performance impact is maybe a little bit like easier when you use the in-chip buffer. So do you have like numbers?
Well, I know that in a paper the numbers were given, but I don't remember. It was not more than 10 to 15%.
Oh, so
But yeah, it's not
that's
that
quite fast. Okay.
Yeah, the overhead comes, well, in my opinion, the overhead comes because the on-chip buffer is very small. So you have to, when it gets filled, you have to store the buffer content somewhere else. So this is why there is an overhead. So we don't have this overhead when we use the TPIU because, well, we have, first of all, we decode the trace as it comes. So we don't have to store it, and we store only the decoded traces.
Great. Okay.
Thanks.
No more questions? Okay, thanks.